Okay, in this video we will discuss on transistor characteristics. So transistor characteristics are crucial for understanding and designing transistor circuit for applications like amplifications and switching. Okay, so these are some of the characteristics we will discuss in this video. The common emitter configuration is preferred for amplifications because it provides high current gain and high voltage gain and consequently high power gain for making a most widely used configuration for general purpose amplifications in the applications like audio and radio frequency circuits. Okay, so in the last video we discussed on there are different configurations like common emitter, common base and common collector. In this for particular applications like amplifications, we particularly used our common emitter configurations. So that we will discuss only common emitter configuration in this video. Okay, this is the circuit diagram for the transistor characteristics. So this is our transistor. We are using a NPN transistor where we also going to bias this base and emitter by a battery, and we also need to bias collector and emitter by the power supply VCC. And we are putting input signal here, which may be a sinusoidal signal or a DC signal, and we should get the output current here. Okay, we are measuring the output current here. Okay, this is the circuit we are using. And if you look at the different type of characteristics of the transistor, the first one is called input characteristics. So if you look at this video, you can see that the input current is IB and the input voltage is across here, that is VB. And if you want to measure the output current, that is IC, and the output voltage is VCE. Okay, so this looking this one as input and output, so we can do different type of characteristics. One is called input characteristics, where the input current is IB and input voltage is VB. So we can draw the character. So this is acts normally like a diode characteristics. And the second characteristic is called output characteristics, where we draw the graph between VC, which is the output voltage, and output current IC. So we will get a characteristics like this, and we get different regions here. The first one is called the cutoff region, and the other is called the active region, and also we have a saturation region. So what you're doing is, you can, if you change your input current like IB, you can control your output characteristics. So that is one of the transistor action. So the IB will determine what should be the current IC for a particular VCE. Okay, this is the output characteristics. And finally we have a transfer characteristics, where we plot the output current versus input current. This is the transfer characteristics. Okay, since this is the most important graph in the output characteristics, we will look mainly on the output characteristics. Okay, so the output characteristics have these features like I discussed in the previous slide. So this is the forward region, where we are applying the forward voltage and measuring the current. So what you do is, you are changing your IB for the different values. What you will get a change with a small voltage here, and it will be saturated to here. Okay, for a particular input current. And the reverse characteristic should be like this, and this will be showing a low current in the reverse direction. We are applying the negative voltage here. Okay. Okay, if you are looking these features, we can operate this transistor in different regions. The first one is called a cutoff region. Cutoff region, we can see that the emitter base junction should be reverse biased. The emitter base junction we discussed in the biasing, it should be reverse biased, and the collector base junction should be reverse biased. Both junctions are reverse biased. We get a region called a cutoff region, and the other region is called active region. This is called the emitter base junction is forward biased, and collector base junction is reverse biased. Okay, this active region we are using mainly used for amplification purpose. So For amplifications, we need a forward biased junction for the emitter based junction, and the collector based junction should be reverse biased. So finally, we have a saturation region. Here is a saturation region where the emitter based junction is forward biased and the collector based junction is forward biased. Both junctions are forward biased. It's called a saturation region. So these are particularly useful when you are using a transistor as a switch. Okay, saturation. So you can directly switch on your transistor, and if you remove this one, both are reverse biased, you are getting 0. So we can get as two states as 0 and saturation region, this one. And when you're amplifier, you have to use the active region, forward biased and reverse biased. So okay, we will try to implement this circuit in the LTspice and see whether we can generate your output characteristics in the LTspice. Okay, this is the circuit diagram drawn in LTspice. So here this is the transistor. We can select the transistor from the components list, and we can give the transistor as 2 and 2, 2, 2, 2. Okay, you also need a current source here. So you can select here, go here and select search a current here, to get a different to get the current source, so that you can select and get the current source here. Then you have to give the resistor. I choose this 1K, so we can give a value of 1K here, and you need a power supply also. Okay, this is a normal power supply that you can choose from here, and you can put it here. Okay, you also need to put the proper ground for this one, and so the main thing is you have to do the simulation here. So this is the simulations we have done. So if you look at this, the simulation, we can use the DC sweep here. So here using DC sweep, and if we have to use two sources for this one. The first source, I have to give a linear type of sweep, It should start with a minus 10 to 10 and with the increment of 0.2. Okay, this is the first source. We vary the voltage, and we also need the second source. This is actually the I1. I1 also we will increment your input current using this one. This is also linear ingression. There are different options like octave, decade, and list, etc. we can do. So we choose linear, and we have to give the starting value. So I give a starting value of 0, and the stop values I can giving a microampere. So you give 50 UA, and you have to give the increment of 10 UA, that is microampere. So these are the two things you have to choose. Okay, so what we do is it will sweep two sources. One is a current, and other is a voltage, to get the required curve. Okay, so if we try to run this button, so we get the output where this is a current source and this is a power, the VCC. So I have to measure the current across this one. Okay, remember that the output voltage is output current versus output voltage. Okay, I want to measure the voltage. Actually we are sweeping this voltage. Then we can see that this is the output characteristics. This is a 0. So we are getting a region where you are getting a different type of this type of slopes and saturations for the different type of input current. Okay, so to look at more closely, I can give only one value. So if I change instead of 50, I'm giving 10. Only particular value, one value instead of multiple values. I'm giving only one value. Let's see what will happen. So if I run my simulations, I'll get a this is the particular curve I get. Okay, after a volt, 2 volt, it will go to saturations. So if I giving a different current, what will happen? It will actually go to another region and it will be saturated to this value. So this is actually the characteristics, output characteristics of the transistor.